Steel Profiles podcast is brought to you by AISC Continuing Education. Visit aisc.org/seminars to find a seminar in a city near you.
Welcome to another episode of Steel Profiles. I'm your host, Margaret Matthew, Senior Engineer in the Continuing Education Department at AISC. My guest today is Dr. John M. Barsom. Dr. Barsom received his bachelor's degree in physics in 1960 and his master's degree in mathematics in 1962, both from the University of Pittsburgh, and then went on to earn his PhD in mechanical engineering, also from the University of Pittsburgh, in 1968. Dr. Barsom began his career at PPG Industries Research Laboratory and then went on to work for U.S. Steel, where he remained for the next 30 years. Through his work, John has become an internationally recognized expert on the properties and behavior of steels, on fracture mechanics, and failure analysis. He is currently the president of his own consulting firm. John serves on the AISC Committee on Specifications, as well as on multiple other AISC committees. He also serves on committees for AISI, ASTM, ASCE, ASME, and many others, as well as serving on many research advisory panels. Dr. Barsom is the recipient of many prestigious awards from many diverse associations, including the AISC T.R. Higgins Lectureship Award, which he received in 2003, and the AISC Lifetime Achievement Award, which he received in 2000. Welcome, John. Thank you so much for taking the time to talk to me today.
Oh, it's my pleasure and honor to be with you.
Oh, we always like to hear that. You were a child in Palestine. Were you born there?
I was born in Jerusalem.
In Jerusalem. And I understand it's a fascinating story how you ended up in the U.S. Can you tell us about that?
Yeah, it's a long story. I'll give you the short version of it.
Okay.
I was born in Jerusalem in a very religious Christian family. My father was a teacher and the principal of our parochial school. Mm-hmm. In 1947, the family became refugees of the Arab, at the time, probably more proper to call it Arab-Jewish conflict, because Israel was not formed at that time. And the family immigrated to Bethlehem. But my father stayed in Jerusalem to take care of the school and had to move the school to the old city, close to the monastery of our church. And he lived at the monastery. While there, the Anglican bishop in Jerusalem wanted to learn Aramaic and came to the monastery and asked if somebody would teach him Aramaic. Aramaic is the language of my family, of my church, and the language that Christ spoke. And my father was an authority in that language. So he worked with Dr. Klein to teach him Aramaic. So happened that Dr. Klein's home base was in Indiana, in the United States.
Oh, okay.
And the church in Indiana had a newsletter. Dr. Klein wrote an article about the church and about my father and about the school. I never saw the article, so I don't know exactly what he said in it, but a family in Pittsburgh, Pennsylvania used to receive that newsletter. They saw it and sent a small contribution to the school. My father, being the principal, had to send a thank you note. That started a correspondence for several years. The family in Pittsburgh lived in a very affluent suburb of Pittsburgh, and they did not have a Presbyterian church there. So they established a church, and after the church was established, they wanted to do a Christian deed. They considered several options, and I was selected to come and study in the United States as their Christian deed. So,
really?
Yes, so I'm deeply indebted to them.
So how old were you when you came?
I was 18.
Oh, okay.
I had already graduated from high school at 16 and worked for 2 years and came to the United States when the opportunity came up.
So then what made you decide that you wanted to stay here?
Well, in my sophomore year, I met a beautiful, smart, vivacious woman, and that was it.
That was it. You also have a very interesting educational background. So your bachelor's degree is in physics and your master's degree is in mathematics, both from the University of Pittsburgh. What were your early aspirations when you were studying these pure sciences?
Well, what people really don't know is that I didn't start in physics. I came here, I wanted to be a civil engineer. And because I had already worked for a couple of years, I was a little bit closer to be with the seniors in civil engineers as friends than with the freshmen my class. They had a seminar course, half credit, where they would go and visit different places to show them what they're going to do once they graduate. And one of the trips was to American Bridge Design Division. And I was asked to go with them. So we went there, and there was a big, huge open space with engineering drawing tables and a person behind each table. So after we walked through part of it, I asked, where are the civil engineers? They thought I was crazy. I said, what do you mean? I said, well, where are they? I said, everyone sitting behind those tables is a civil engineer. Well, at that time, I decided that's not what I wanted to do the rest of my life. So the question was, what do I want to do? And that was the time of Sputnik. I was caught up, like many others, in space and space exploration. So I went into physics. And I really wanted to continue in physics. I got my bachelor degree in physics, but once I graduated, I couldn't expect my sponsors to continue to support me. And I had already decided that we were going to get married once my future wife, finishes in 1 year. So I had to get a job, and we both were going to go to graduate school. So I decided she'll go full-time and I'll go part-time. But physics didn't have night classes, so the closest to physics was mathematics.
Math.
So I went to math.
So then you went on and earned your PhD in mechanical engineering. So why did you make that choice to get into engineering then as your PhD study?
Well, I really enjoyed mathematics. I had a wonderful advisor for my master's degree. I did my master's degree in geometry of the complex domain, which is four-dimensional mathematics.
Oh my.
And I can draw pictures in 4 dimensions.
Oh, I might have to have you show me how you do that.
So I thoroughly enjoyed it, but I really wanted to get my degree in applied mathematics. I took all the applied math courses. I didn't have enough for a PhD, and I didn't want to go into non-applied mathematics. So I figured I want to do things. So the closest thing was to go into engineering. And civil engineering was already out of the picture because I didn't want to sit behind the tables. And I looked at mechanical engineering. It has orbital mechanics and fluid flow and stresses, strain, deformations, designing equipment. So I went into mechanical engineering to do things.
So you wanted to apply what you already knew, and
That's what I always wanted to do, is work with it, do
Work with
something.
it's fascinating that you're so well known in the metallurgy field, and your work on fatigue and fracture mechanics has had such a huge impact on the structural engineering field, and yet you didn't ever study metallurgy or structural engineering.
That's correct. The thing is, I was very fortunate. When I started working at U.S. Steel, I didn't have any knowledge of what steel is, and I had to learn very fast. So there were several things. One is I sat down and I studied on my own. But also, I had the best metallurgists anywhere as colleagues. And all I had to do is ask. And they would answer, and I asked a lot, and I learned a lot from them. Also, U.S. Steel had in-house short courses, and I took courses in steel making, in continuous casting, in heat treating, took all kinds of courses so that I tried to fully understand what makes steel, what it is, what the microstructure is, what the defects in it how they come about. So I was very fortunate to be in the right environment. In terms of the structural engineering, I was also fortunate that in my mechanical engineering I had the background to understand what the designers would tell me. And at one time, between 78 and 83, I was a division chief, and one of the sections was a design section. So I had to know what they are telling me they want to do research on, and had to review their work. So I had to sit down and learn as much as I can about structural engineering. I definitely am not a structural engineer.
So you talk about working at U.S. Steel. Your first job was actually at PPG, which is Pittsburgh Paint and Glass Industries Research Lab, where you worked in glass research. So did what you learned working with glass then help you in your later research with steel?
Yes, actually, one of the projects I was assigned was to try and figure out the size of glass particles when a side window on a car or the back window on a car breaks. It breaks into very small pieces. And the government had a regulation as to what the maximum size of these particles should be. Because if it breaks, they didn't want the occupants to get harmed.
Sure.
So I was asked how I would combine the processing of glass, which is tempered glass, where they put a very high compression on the outside surface and very high tension on the inside, and its fracture characteristics, to come up with the controls on the quenching and tempering of the glass that would give them the right size particles. Well, there was a gentleman in France who had written 12 papers on it, and still we didn't have an answer. And I didn't know how to approach it, and then I saw a brochure about fracture mechanics short course that was going to be held in Denver. And that fascinated me. I figured maybe that will get me some handle on how to analyze it.
So that was the beginning of fracture mechanics.
That was the beginning of fracture mechanics. I went to Denver. I sat in the class. I wrote the equations for the solution, came back to the lab, and within a month I had the experimental data to support the conclusion and solve the problem.
Wow.
And that was my first getting my feet wet in fracture mechanics, and I was hooked on it.
Hooked, yes. So then from there you did go to work for U.S. Steel. So how and why did you go from glass research to the steel industry?
Well, actually getting that first experience in solving the problem in fracture mechanics for the glass was a turning point in my career. I figured that to really apply it in a more broad sense, I need to get into the steel industry, because that's where many things are going to be using fracture mechanics. It was a brand new field, and U.S. Steel had a big contract with the Navy to develop future submarine hull materials. And they were hiring, so I decided I'll go there and see if I can use fracture mechanics and apply it to understand steel and how to apply it. So I went and started working at U.S. Steel.
So that's interesting. The fracture mechanics really did drive your career path.
Very definitely.
So then you stayed at U.S. Steel, where you worked for the next 30 years in research, eventually being named the Director of Materials Technology and then Research Fellow due to your outstanding contributions to U.S. Steel and the entire steel industry. So what do you think were some of your most important contributions at U.S. Steel and to the steel industry?
Well, for U.S. Steel, they really encouraged me to continue to do the work that I was doing, because it was both new, because the field was so new, and also it helped in extending the life of components and understanding failures in the plants. For example, I did research on how cracks initiate from notches. And that I was able to apply to a rolling mill housing, where it's a big, huge structure. It had a crack in it. to replace it would cost $2 million and would take 1 year of delivery, and they couldn't afford to do that. So I was able to apply what I learned from my research to arrest the crack, and it made it last for many, many years. I know it was still operating when I retired.
Really?
Yeah.
Wow.
The other thing was, another example is I worked on an ore bridge that the design people wanted to tear it down, that it had seen its useful life. The mill didn't want to because they needed it badly, and I was asked to extend the life of the structure for 5 more years. I did the work and applied what I learned in my research, and it lasted 25 years, and then they tore it down, not because it broke down, it's because it became functionally obsolete. So they did appreciate applying what I learned to solve some of their problems. In terms of the industry, I was the chairman of the Transportation and Infrastructure at AISI, and I think the one thing that I am pleased about is that I was able to use my research results to come up with the requirements, Sharpie requirements for bridge steels, which was adopted by the AASHTO and by ASTM. So that was big help for the steel industry. But I also pride myself that as chairman, I always represented all the steel industry, regardless of who really was doing what. For example, I pushed very hard to have design examples in the Highway Design Handbook on short span bridges, which would benefit the structural shape producers more so than the people that build up beams. Yet the structural shape producers were not members of AISI at the time. So it didn't matter to me as long as all the steel industry benefited. That was just fine with me. So I tried to serve everybody. I guess it's appreciated. It was appreciated.
Sounds like it. I understand that you worked with many of the early pioneers in the fracture field. Can you tell us about some of them and what it was like to be involved in the pioneering days?
That was really a pleasure to be with the ones who really started the whole field. 2 people stand out. One of them is called the father of fracture mechanics. He's the one that started the entire field. His name was George Irwin. George was a very, very bright, very gentle man, always with a beautiful smile. Got to know him very well, encouraged me a great deal to continue my research when he saw the results. Got to know him, got to know his wife, been to his house. That was very rewarding to me and very encouraging. The other person is Paul Paris, Dr. Paul Paris. He was at Lehigh at the time. We have the Paris power law in fatigue crack propagation. He's the father of fatigue in fracture mechanics. Again, he was almost a mentor. He wanted me very much to go and get my doctorate with him at Lehigh, but circumstances were such that I didn't want to move out of Pittsburgh. But I also got to know him and his wife at the time and have worked with him even after he left Lehigh. He's now at Washington University in St. Louis. It was a very rewarding time and an honor to work with these people.
During your time at U.S. Steel, you also co-authored a steel structures textbook. Fracture and fatigue control in structures, applications of fracture mechanics. That's been used in about 50 universities in the U.S. and abroad, as well as extensively used by practicing engineers. It's now considered a classic. Is it still in use today?
It's still in use today. I don't know how many places are using it, but I see it in hands of practicing engineer quite often and get myself in trouble when they tell me, but you said this and that in your book.
Well, that's great though. If you see it, the practicing engineers have it, it's obviously useful. not just as a text, but in practice. So it must be very practical, not just for use as a student.
As a matter of fact, that was one of the aim of really writing that book, is to make it a very practical, handy kind of a book in the hands of practicing engineers. For universities, it's usually on the senior and master's level, so it's used much more by practicing engineers than by students.
You have an international reputation in your field. Can you talk about the work that you've done outside the U.S.?
I've done work in Germany, I've done work in China, done work in Brazil, done work in Venezuela, done work in Puerto Rico. So I've done a few things outside.
A few things, You've also conducted a variety of welding research and are a certified weld inspector. Can you weld?
No.
I asked Wayne Miller the same thing. Can you weld? Are you a good welder?
No, I cannot weld. I did not try.
As you mentioned, you were the chair of AISI's Transportation and Infrastructure Committee for almost 20 years. And I understand that during your tenure in that position that the HPS 70W was developed?
Yes, it was.
Can you tell us about that?
In 1992, AISI partnered with the Cardrock Division of the Naval Surface Warfare Center and with the Federal Highway Administration to try and develop new high-performance steel for bridges. A team of experts from the steel industry, from welding, from the Navy, from professionals, from academia, were joined together to come up with the best composition for the material. And I would have to give credit to one individual who probably contributed most of all, and that's a metallurgist by the name of Sam Manganello, who really contributed a great deal to that development. That effort was very successful. We ended up with a 50W, which is weathering steel, W for weathering. We ended up with 70W and with 100W. These materials have been used now in over 400 bridges in 43 states. They are saving cost and saving weight and produce much better steel for bridges. The economy is great that way for steel industry. And within 5 years from concept to application, it was all done. And because of that effort, the Civil Engineering Research Foundation awarded the Charles Pankow Innovation Application Award to the team of AISI, U.S. Navy, and the Federal Highway in 1997. So that was really a great accomplishment on the part of all the participants.
Mm-hmm. So this was really quite a breakthrough for bridge construction.
Very definitely. Very definitely.
You also received the T.R. Higgins Lectureship Award from AISC in 2003 for your lecture, Structural Steel Failures, Effects of Joint Design. What were your key findings?
Key finding is be careful with details. Structural details.
Structural details.
They are the ones that cause the problem. If you attach a small piece to a structure and as a lifting lug and you leave it there, it becomes part of the structure. You can't ignore it. It may cause fatigue cracking and failure. If you have a transition between one size and another, make it as gentle as you can. If you have a radius at a keyway or someplace else at a weld access hole, make it as large as you can. All of these will help you have a safe and reliable structure. It's when we don't do that we end up with structural failures.
Mm-hmm. You've also been the recipient of a plethora of other awards during your career, including AISC's Lifetime Achievement Award in 2000, and awards from AISI, ASME, ASTM, NIST, and many others. Was there one award or honor that was really special to you or meant more than any of the others?
I think there are two. The first one is the AISC Lifetime Achievement Award. And I say that with all sincerity because I received that award at the same time as Bill Millick and as Bob Disquay.
Oh.
To receive that award with such big giants was a real honor and a humbling experience.
Yeah.
I treasure that a great deal. I think the other one is a combination of things. To be recognized by colleagues and elected as a fellow in 4 technical societies that are very diverse, from ASTM International to ASM International to AWS to ASME, that's an honor I don't know if I really ever would have expected.
And you're so diverse in the things that you've done, and that really shows that all these different organizations recognize that.
Yes.
Tell us about some of your most interesting projects to date.
A lot of I retired from U.S. Steel in 1999, and most of the things I've done since then, I either had to sign a confidentiality agreement or by court order cannot talk about them.
So you can't tell me about your most interesting projects.
So what I have to do is go back. I would say that probably in research, the most rewarding and interesting research I did was the discovery that the fracture toughness of steels, constructional steels, goes through a transition with temperature, that at a given temperature, the toughness increases significantly. Then the next step was to find out the effect of loading rate, how fast you apply the load on that entire toughness transition curve, and to be able to tell where that curve would be on the temperature scale for any loading rate, and then correlating that data with Sharpie and use that data to come up with the requirements for steel bridges, which ended up becoming 709. That has had a big impact. The other part of that research was to relate those curves to the microstructure on the fracture surfaces. And that has been a big help in analyzing failures. So that part was very rewarding in its application. I think in terms of what I like as a research project is one that hasn't been used much. To me, it is the whole process of coming up with the idea and then executing it and ending up with a very, what I would consider beautiful research work. It's almost like someone going through the creative process of writing a poem or making a painting. And that work was on effect of environment, water, on the fatigue behavior of cracks in steel. That whole process of how I went at it, to me, is one that I really enjoy a great deal thinking about it. But that's research. The other parts of my work is really try to prevent failures. And I'd say 1/3 of my work now is that kind of work. Is, for example, a fabricator having initially on a big, huge project, having problem with finding small cracks in the welds. And the question was, what's causing these cracks? And how to avoid them. And I was able to go through the whole process, metallurgical investigation, finding out what the cracks are, how they formed, and what the fabricator had to change in his welding parameters and welding procedure to get out of that problem. And that worked out very nicely. So that's kind of work I'd rather do to avoid failures than having to worry about failures.
Or to figure out why something failed after the fact, but to be able to prevent them ahead of time.
That's right.
Yeah,
and that's
great.
what I like fracture mechanics to be used for, is to avoid things rather than applying them after something broke. But unfortunately, I do a lot of work on why things break.
Why things break.
And I've done a lot of them, some very large structures, TV towers, blast furnace that blew up, many others that I can't talk about.
But I guess if once you figure out why, though, and then we have that knowledge then, and it can be applied then to future projects so that it doesn't happen again.
You hope that there is a transfer
Yes.
of information. Unfortunately, many times there isn't such a thing.
Well, that is too bad. You were very involved in the research after the Northridge earthquake. Can you tell us what your research focused on?
Well, I was on the SAC advisory panel, and one of the things I was asked to do is to look at the failures of components that were tested at University of Michigan and at Lehigh University. And I looked at them, and in essence, what it ended up with the ones at University of Michigan, I wanted to find out where fatigue cracks started, at what locations. I found out that the crack started at the web to flange intersection at the weld access hole. That was one location. Cracks started from the thermal cut surfaces, which were very rough, and they started at the weld toe, and they also started from weld defects. And looking at the whole picture, looking at all the tests, about 90% of them had fatigue cracks at the beam cope hole. And then about 50% of them had at the weld toe, and the others were 20%. So it became very obvious that one of the big problems is the weld access hole. Lehigh did their work with a very good access hole geometry and a good thermal cut surface. So in their case, it ended up 80% of their failures were at the weld toe, and the other 80% were at weld defects. In essence, there were 4 locations where you can be in trouble. You eliminate the worst one, it goes to the worst one that remains, and you have to now worry about all 4 of them. The second part was some of the failures were divot failures, where a piece was taken out of the column, and others severed the whole column. And the question was why. So I investigated that and related it to the stresses in the beam and the stresses in the column, and showed why one would start one way and the other would start another way, and also looked at the microstructure of how the crack started. And interestingly, the crack always started ductily in the weld metal, but because it is a low strength material, it's supposed to, once the crack starts, it's supposed to go very fast and brittly. So that was another thing that I was able to show, and show the effect of the backing bar notch, if you will, because the backing bar was there. So it was an interesting exercise to find out why these components were failing.
We learned so much from Northridge.
Yes, we did, and I think we have a very good system so far.
You've also been an adjunct professor at your alma mater, the University of Pittsburgh, since 1992. What's the best advice you have for students that are graduating and getting ready to enter the professional world now?
Make sure you understand the effect of the details that you put in your structure, and try to avoid having ones that will cause fatigue failure.
Of course, we want to avoid fatigue failures. It's always in the details, though.
Yes.
You know, it's always in the details.
The devil is in the details.
The devil is definitely in the details. I understand you're a very proud father and grandfather. Can you tell us about your family?
Yes. I have my wife, Valentina, is the smarter of the two. She was retired as a professor. She's the linguist and the literature person in the family. Her bachelor was in French and German. Her master's was comparative literature, French and Russian, and her doctorate is in Russian language and literature.
Wow.
So she is the brighter one of the two of us. She raised 2 wonderful daughters who are very smart, very well educated, and outstanding mothers. Each of them has 2 kids, and we see the grandchildren almost every day.
Oh, that's
We're
nice.
very lucky. They live in Pittsburgh. And that's the part where, unfortunately, my work sometimes prevent me from spending more time with the family.
So how old are the grandchildren?
The eldest is 17.
Oh, getting ready to go to college.
Yes. The two middle ones are 15 within 2 weeks of each other, from the two daughters, and the youngest is 11.
So did either of your daughters or any of the grandkids going to follow in your career footsteps?
Let me see. My daughters didn't. My older daughter has a master's degree from CMU, Carnegie Mellon University, in School of Urban and Public Administration.
Oh, okay.
The younger daughter has a doctorate in microbiology and genetics. So neither of them followed my footsteps. I know that my 17-year-old is going to follow probably his grandmother's path. The two middle ones, it's hard to tell.
Yeah.
But I don't know if any of them will become an engineer.
So what are some of the challenges and rewards that you find in your work?
I think the rewards are the whole creative process. Be it a research project, be it a solving a problem, putting a failure of a structure together, that whole creative process, that whole mental exercise. I find it very challenging, very interesting. I think if I were to answer another part of this question is my biggest regret.
Oh, okay.
And that is the many birthdays, anniversaries that I missed because of my job. The times when I should have been home, but I thought that I had to go. And thinking back, some of them I had no control over, I had to go. But many others, I think I could have skipped and nothing would have happened. And that is my biggest regret.
Well, and that's good advice to all the listeners, that work is not always the most important thing.
That's right.
So I have one final question for you. What's the one thing that you know now that you wish you had known at the beginning of your career?
Family should come first.
That's a fantastic answer.
Thank you.
And so simple. Well, I think those are all my questions for you today, John.
Thank you. It's been a pleasure.
Thank you so much. It has been a pleasure. Thank you.
Thank you.
This has been a presentation by the American Institute of Steel Construction.
Join us next month when my guest will be Dr. John Fisher, Professor Emeritus of Civil Engineering at Lehigh University.
For more information on AISC continuing education opportunities, please visit us on the web at aisc.org/seminars. And remember, there's always a solution in steel.